So in order to do that, I looked through my bookshelf, and I found all these books, and they all bring back these memories. So this book was written in 1973 by Marty and Victor Gellman, Stable Mappings and Their Singularities. Michael Singer mentioned it yesterday. My memory is I spent my last year of graduate school reading this book, and a lot of what I know today comes from it. I was just checking with Michael Shearer. He did the same thing about a year later. This one is Singularities and Groups and Bifurcation Theory by Golubitsky and David Schaefer, who's at Duke. I guess Marty used to be a frequent visitor to this area while they were writing this book. And at that time, I was going over, Schaefer was trying to learn about applied mathematics. He was giving a series of very interesting courses that I went over to several times every week. A fair percentage of what I know today about applied mathematics came from that. That's where I actually met Michael Shearer for the first time. One that was not in my office is Symmetry and Chaos, which has the beautiful pictures that were shown yesterday. Some years ago, Marty gave a talk, and before the talk, I took that book to some guy whose name I forget, who's in textile design. And I tried to convince him he should come to this talk because this book certainly had the secret for computer-aided textile design in the 21st century. I'm not sure anyone has ever really picked up on that. That's at home. And another one I found in my office is Fearful Symmetry by Marty and Ian Stewart. And I think it was this book that inspired me to ask Marty one time, how do you write all these books? And he said, well, the main thing is you get Ian Stewart for a collaborator. Which it must be some exaggeration of these other books. Anyway, so I'm sure whatever Marty's going to tell us about today will be very interesting.
Thanks a lot, Steve. I'm not sure where to go from there. But it is true. If you, there are a few people that you get to know in the course of one's career, just phenomenal writers, and Ian fits into that category. By the way, I assume I'm okay without a microphone? Yeah. Okay, so I wanted to pick up on some of the things I was talking about yesterday, the animal gates, because in the discussion, I skipped over a rather important mathematical point, and the first half of the talk is going to be about that mathematical point, and then the second half will be using the mathematics that we've developed to apply to another area, another unlikely area for symmetry breaking, and that is psychophysics and binocular rivalry. So there'll be a little bit of this and a little bit of that in the talk. Something that I also wanted to mention is that at MBI, we very much want to encourage research that is bio to math. So everybody thinks of the interface between mathematical biology is that you use mathematics to study models in biology. But we would also like to encourage what we think will be very much a growth industry of how the problems in biology lead to interesting mathematics. So it should go both ways. The diffusion from bio to math is going to be much slower than math to bio, but both are important. And I hope that this talk will have a little bit of both of those elements. Okay, so I mentioned animal gates, and for those of you who might not have been there yesterday, just very briefly, standard gates are things like the bound, where front legs hit the ground, rear legs halfway through the gate, front, rear, front, rear, front, rear. Now, the thing to observe is that the left legs and the right legs are moving synchronously. They're moving together. So, however one's going to describe this gate, you're going to want this equality of motion somehow of the left and right to be there. Also, the front and back are moving exactly a half a period out of phase with each other. even though the front legs and the rear legs are somehow mechanically not quite the same, nevertheless, the motions have this. And I mentioned in the talk that one way to get this kind of synchrony and phase shift synchrony is through symmetry. And so the first part of the talk is going to include, well, how does that actually happen? What's the mathematics behind phase shift synchrony and symmetry? The various gates that I mentioned are summarized here. The walk is this left rear, left front, right rear, right front, and it's a it's a 4-count gate. But what it means is if I permute the legs, left rear to left front to to right rear to right front, there's a quarter period phase shift in what's happening. Now, what does that mean for a system of differential equations? It means that if you look at the time series in some sense of the leg motions, then you can superimpose on them. You can superimpose them if you shift the phase a little bit. They'll be exactly superimposed. And we said, well, how does this come about? I think I flashed up this slide, which has the network, doesn't matter, I'll flash it up right now. It has a network of differential equations, coupled system of differential equations, given this architecture. And we want to know that we can get periodic solutions to the differential equations associated with this architecture, which have the same symmetries, phase shifts, synchronies, as the gates that we were talking about. And what I didn't say is that we constructed this network using symmetry. That is, if you're going to have a walk, there should be this fourfold symmetry. So there should be a Z4, omega, the fourth is the identity. We have bilateral symmetry, that's the kappa. So Z4 cross Z2 is the simplest symmetry group, which would include what we see in the gates. And we wanted the symmetries to be reflected in this network, which is going to produce the gates. So we're making an assumption, a basic assumption, that the only way that you can get these phase shift synchronies to occur, and now I'm going to add an extra word, in a rigid way, and I'll explain or a robust way, what I mean by that in a second, is if symmetries are present. So what do I mean by rigid? We don't know what the differential equations are that are associated with this network. Certainly, even if you knew the form, there would be, like you assume that these are Hodgkin-Huxley equations or something of the sort. There are lots of parameters in there, and you don't know exactly which parameters to choose. So, without knowing the differential equations, we still want this, say, quarter period phase shift in the walk to be present. So what we expect is that we have a periodic solution. If it's a hyperbolic periodic solution, so that if you perturb the system, you maintain the periodic solution, we want the phase shift to still be exactly that quarter period. And this comes about because of symmetry, to come in a moment why. We claim this is the only way. So the first part of the talk will have two parts. The first will be to explain why what I just said is false, and the second to explain why it's true. And then you can decide which one you like. No, they're both true. Okay, so let's set up the mathematics a little bit. So these coupled systems of differential equations are given by network architecture, which are these graphs over here. And the simplest graph is I have two identical systems of differential equations. x1 and x2 are the state variables of the first node and the second node, and they can be k vectors in general. The first equation is x1 dot is the sum function of the internal state variable, x1, and the coupling variable, x2. It's coupled to x2. The fact that these are the same nodes means that we're coding x2 dot to be the same f, but now of x2, x1, because the internal state variable and the coupling variable have swapped roles. If I take this network architecture of a bidirectional ring, then I have the same sort of thing, that x1 dot is a function of x1, the internal state variable, but there are two coupling variables, x2 and x3. But in fact, I know more, because there's only one kind of arrow in this. This is our coding for it. It means that the couplings are the same from 2 to 1 as from 3 to 1. So I can swap x2 and x3, and I don't change f. These are symmetry properties that come in. Now, so this first network has Z2 symmetry, swapped 1 and 2. The second one has full permutation symmetry of the nodes. Here's a network that has 5 nodes. It's a unidirectional ring of 4 nodes with a 5th one sending its signal to each of the other 4, but receiving it back from 1 and 2. This network has no symmetry. Nevertheless, the collection of differential equations is given as I've put down over here. Now, somewhere, if you're going to talk about differential equations associated to a network, you have to have some way of codifying the kinds of differential equations that come up when you have a certain network. And that's what's going on here. We call these admissible differential equations associated with these networks. And I'd like to talk a little bit about the kinds of solutions, particularly periodic solutions, that you get when you have different network architectures. Okay. So these gates, there were 2 kinds of synchrony. Synchrony where the output to 2 nodes was identically the same for all time, just same thing, and this phase shift synchrony where the solutions were the same if you move the time series and superimpose them one on the other. So let's talk about the first kind first. Suppose that I have an n-node network, and I'm going to say a solution exhibits partial synchrony if there are 2 nodes, C and D, for which the time series are identical. And a polydiagonal, just by definition, is a subspace of phase space which is given by a certain subset of coordinates being equal. So pairwise, you have a certain number of pairs of cells for which xc equals xt. And we'll call a polydiagonal a synchrony subspace if it's flow invariant for each of the admissible vector fields associated with a given network architecture. So we choose the network architecture and ask what are going to be these flow invariant subspaces. And if you have such a subspace, why should they exist at all? Then all solutions in the synchrony subspace exhibit partial synchrony by definition, because certain nodes are always going to be equal. And that's the definition. Okay, so what's a symmetry of a differential equation? Definition, it takes solutions to solutions. That's the basic thing. So it's an operation. Usually we think of it as a linear map on phase space, which takes solutions to solutions. And this is a back-of-the-envelope calculation to show that if it takes solutions to solutions, if sigma is a symmetry, then the vector field f of sigma x is sigma f of x. So the vector field, which is nonlinear, commutes with the linear map sigma. Now, let's do a little bit of, use a little bit of group theory and symmetry. Fixed sigma is going to be all of the points in phase space for which sigma x equals x. And of course, this is it's a homogeneous linear system of equations, so the solutions is a subspace. Fixed sigma is a subspace. It's always flow invariant. Why? If I start off with x, which is in here, and let sigma be a symmetry in capital sigma, then f of sigma x is f of x, because sigma fixes x. But since sigma is the symmetry of the differential equation, it's sigma f of x. So you have this linear subspace. At every point in the subspace, the vector field is tangent to the subspace. So when you integrate a system of differential equations, you stay in the subspace. So it's flow invariant. Now, on the other hand, if I have a symmetry of a network, symmetries of networks are all permutation symmetries. They just permute the nodes in some manner or fashion. So what is going, let's just take an example. Suppose you have this 4 node bidirectional ring, and you have a permutation which is going to be a symmetry. The permutation is interchange 2 and 3, interchange 1 and 4. That's the same as rotating this by 180 degrees, but I want to think of it in terms of permutations. What are the fixed points of 2, 3, 1, 4? Those are exactly the points in phase space for which x2 equals x3 and x1 equals x4. That is, the fixed point space of a polydiagonal, the fixed point space of a permutation is a polydiagonal. If the permutation is a symmetry, then you get a synchrony subspace. So these kinds of symmetries give you synchrony subspaces. Synchrony subspaces say that there are lots of solutions which exhibit this partial synchrony. I should go around. Okay. I'd like to look at a network which has no symmetry, but which does have a synchrony subspace. So this unidirectional ring of 7 nodes, notice 1 sends its signal to 2, 2 to 3, and so on, but 3 sends its signal back to 1. So every node is receiving one signal from somewhere else. And I colored these nodes green, sort of pink, and sort of blue in some manner. They show up. Okay, so now the green nodes, x1 dot is a function of internal state variable x1, and it receives a signal from x3, so x3. The green dot equation here receives its input from x3 also. It's f of x4, x3. This other green 7 receives its signal from 6. Notice that the internal state variables are green when you chose them, but all of the coupling variables are blue. And similarly, pink dot is f of pink green, blue dot is f of blue red. That is, blue receives its signals, or pink receives its signals, to 6 from 5, 3 receives a signal from 2. So if I restrict to the polydiagonal, all the green coordinates equal, all the pink coordinates equal, all the blue coordinates equal, then this is a flow invariant subspace. It's a polydiagonal, so this is a synchrony subspace. Now this is just a special case of the general theorem. And the theorem says if I color the cells in, you're given a polydiagonal. So a certain subset of coordinates are equal. When 2 coordinates are equal, color the cells the same color, if and only. So I can go from a polydiagonal to a coloring. I'm going to call the coloring balanced if every node, every cell, receives the same number of inputs from cells of each color. Okay? And if the coloring is balanced, theorem, the synchrony subspace is, the polydiagonal is a synchrony subspace. And this is if and only if. So what I've just described here is a theorem which takes dynamics about these admissible systems and reduces it to a combinatorial condition on the network architecture. So from network architecture to dynamics, do not stop, do not, or I guess do pass go. And it's lost. So let's take this 2-node network, the simplest possible coupled system, and let's ask, well, what about time periodic solutions? Well, it's not surprising since x1 equal to x2 is a flow invariant subspace for this system. Do it by symmetry, do it by coloring, either way, you're going to get that it's flow invariant. We know that we could get periodic solutions in that subspace, so getting periodic solutions that are synchronous is not a surprise. But can we get periodic solutions that have certain kinds of phase shift synchrony? And so I'd like to say, I'm going to say yes, you can get solutions where the second node is 1/2 period phase shift from the first node. And that this is a rigid thing, so it's not surprising that it occurs. So how do we do that? Let's take a hyperbolic T-periodic solution to an admissible system, in general, and suppose that gamma is a group of symmetries of network. In fact, in this case, you don't have to be on a network; it just be you have symmetries on some phase space. I'm going to let H be those symmetries in gamma which preserve the trajectory setwise. So it doesn't necessarily preserve it pointwise, but just setwise. Then suppose you have such a symmetry, gamma, then gamma x of t is a solution, because remember, symmetries take solutions to solutions. On the other hand, gamma x of 0 must be on the trajectory by the assumption that gamma is in H. So therefore, there is some theta, fraction of the period, for which gamma x of 0 is x of theta t. But now I have two solutions, gamma x of t and x of t plus theta t, which have the same initial condition, so they must be equal for all time. So now I have a spatiotemporal symmetry that if I apply gamma to the solution, it's the same as phase shifting it. Okay? So symmetries in this context, these spatiotemporal symmetries, do in network going to correspond to phase shifts of coordinates. So let's go back to this example up here. Gamma is, the symmetry is swapped 1 and 2. It's an order 2 symmetry. If I apply it twice, I must come back to the identity. So twice theta must be 0 mod 1, 0 mod 1, since this is a fraction of the period. So the only possibility is theta is 0 or theta is a half. That is, the only kinds of periodic solutions that I can get with special phase shifts are going to be with 0 and a half, a period phase shift. That comes from symmetry. It's rigid in the following sense. If I perturb the periodic solution, then I'm going to get a unique periodic solution nearby. When I apply gamma x of t, I better get the same perturbed period, or else I have two periodic solutions that are nearby, and that trajectories, and that does not allow by hyperbolicity. So hyperbolicity implies that this theta equal half is in fact a rigid phenomenon. So this is the kind of thing that we wanted for the gates. Symmetries in the network are going to correspond to periodic, you'll get periodic solutions with certain well-defined phase shifts and certain well-defined synchrony. And this is exactly what we needed to define the gates. Okay, so what about this bidirectional ring of 3 cells? Well, suppose H is generated by the permutation, which takes 1 to 2 to 3 back to 1, and the phase shift is 1/3. That's possible on this. Then x3 of t will be x2 of t plus 1/3 of a period, which is x1 of t plus 2/3 of a period. So what's that going to look like? Well, it'll look like a periodic state where you have the blue cell, the red cell, and the black cell, and they're just 1/3 of a period out of phase, and these are not sine waves. These are real, honest solutions to these kinds of nonlinear differential equations which come up. Similarly, I could have a solution where I swap 2 of the nodes, x1 and x3, and I have a half-period phase shift. That's possible. x3 of t is going to be x1 of t plus a half a period. But a little bit of a surprise, x2 of t is x2 of t plus a half period. That is, x2 must have twice the frequency. And that's forced by symmetry. Here's the red cell and the blue cell, black cell, half a period out of phase from each other. The blue cell oscillating at twice the frequency. So these kinds of phase shift synchronies, absolute synchronies, even some multi-frequencies, are forced by symmetry when you look at these various networks. Okay, now, so that was one part of the discussion. We have these synchrony subspaces, and we have periodic solutions coming from symmetry, which exhibit this rigid phase shift condition. now I want to go back and give you another part of this theory of coupled cell systems, and I should say that it's work that's been going on with Ian Stewart for the last 10 years and a number of other people whose names will pop up as we go along. Suppose I take this bidirectional ring and take the polydiagonal where x1 equals x2. They're the red cells, and there's one blue cell. You could get this by symmetry, but let's use balance. Red receives a red input and a blue input. This red receives a red input and a blue input. It's balanced. Blue is a singleton, so it's always balanced. So this is a flow invariant subspace. So let's look at the differential equations on that subspace. x1 dot is a function of x1, but x2 equals x1 and x3. x3 dot is f of x3, x1, x1, again, because x2 equals x1 on that subspace. Now, this is a collection of systems of differential equations that corresponds to this very peculiar network architecture where you have red being self-coupled and receiving the coupling from blue, and blue receiving 2 arrows from red. Notice, red receives a red input and a blue input. Blue receives two red inputs. So even though you start with nice-looking networks, you can end up with self-coupling and multiple arrows coming out of this. And this turns out to be the right, shudder to use the word, category of graphs in which to talk about network dynamics in. Okay, we call this network the quotient network, and there's a second general theorem about the dynamics. If you take any admissible vector field with respect to a quotient network, then it lifts to a vector field, admissible vector field on the original network, which it's admissible. So that means I can find out information about vector fields up here by looking at vector fields down there. And I'd like to show you an example. This was the 5-node network that I had on the first slide. I said it has no symmetry. I won't prove that to you, but it's true. Notice that we colored the cells blue, black, and red. This is balanced. The blue cells receive a black and a red input. This blue receives a black and a red input. Black receives blue and red. Black receives blue and red. Red is a singleton. This is balanced. So this corresponds to a flow invariant subspace. Well, what's the quotient network? We get the quotient network by looking at the colors on the original network. So we had 3 colors up here. We want to know how red dot evolves, blue dot evolves, and black dot evolves. Well, this bidirectional ring, we know has solutions, or can have solutions, where 2 of the nodes are half a period out of phase, and the third is twice the frequency. Well, we saw that as a possibility. So in this case, here we have the blue nodes are synchronous. They have to be for being on the quotient network. The black nodes are synchronous. But notice that blue is half a period out of phase from red, and black is going at twice the frequency. So this kind of solution appears on this network because of the asymmetry on the quotient network, not because of the symmetry on the original network. Something else which is kind of amusing is that here I took red and blue as being the symmetric one, swap red and blue, but I could just as easily have swapped blue and black. And then I would get a solution where the blue nodes are half a period out of phase from the black nodes, and the red node is twice the frequency. I dare say it doesn't look obvious that these 2 solutions must coexist on the original network. The only difference is a change in initial conditions. So if I start with an initial condition up here to get this solution, I can just swap the nodes here, and I'll get the initial conditions for that solution. So when you look at the time series in the nodal coordinates, it's not exactly picturing what you might be thinking of going on in the big phase space. So, but some of this theory does help you to do that. Now here's a theorem which Yunjiao Wang and David Romano were able to prove about 2 years ago now. And Ian Stewart had more or less conjectured he conjectured the statement of the theorem. It took about 5 or 6 years to get a proof of this. I'm actually quite pleased by having been able to get it to completion. And here's what it says. Suppose you start with a hyperbolic periodic solution on a transitive network. So the transitive network is from every node I to every node j. You can get there by following a sequence of couplings, a sequence of arrows. So that's a transitive network. And suppose that you have a solution which has a rigid phase shift synchrony between two nodes. Okay, so it has some phase shift, third of a period, whatever, and that it's rigid that if you perturb to an associated, to a nearby admissible vector field, you get a periodic solution with the same phase shift. Then there is a quotient network and a symmetry on that quotient network which generates that phase shift. So in the previous slide we have examples of rigid phase shift synchrony, though symmetry, but it came from symmetry on the quotient network. What this theorem is saying, that's the only way it can happen. So this gives us some confidence that in doing the modeling for the gates, assuming symmetry was actually not a bad assumption. In other words, we want these platonic ideal of what is a walk or a trot or a pace. These gates are defined by phase shift synchronies. Therefore, we want any network model for a central pattern generator for such things must admit the symmetries, at least on a quotient network, to force that thing. So the modeling does, in fact, follow the way that people describe these gates. Okay. Time for a rest. Now I'm going to just switch switch directions, but I don't know if anybody has any questions about this. Yeah.
So you haven't said anything about the vector fields except that they have symmetries.
Right.
And then there's a sort of an assumption that they support a periodic solution.
Yes.
And that periodic solution is hyperbolic.
Yeah.
So then I can just dream up my favorite nonlinear oscillator that has that property, and then write down a whole system, the whole network system,
Mm-hmm.
the symmetries, and then the
Yeah, it's not the case that that an individual node has to oscillate on its own.
right.
So it's a little bit more complicated than that. But the theorem is if and only if. In other words, you can classify all hyperbolic periodics, all kinds of phase shift synchrony by these symmetries on quotient networks. So there are vector fields which have these solutions,
Right.
as well as if it had this solution, it would have this property. So, now, it doesn't mean, but it's an important point which is kind of implicit in what you're saying. It doesn't mean that every vector field has a periodic solution of all of these different types. We're just saying the menu of possibilities is given by this structure of symmetries on quotient networks.
Okay, so no, all right, that sort of gets at my question. That
Yep.
if I have a network and I have a periodic solution that lives on
An admissible
an
vector
invariant-
field.
yeah, an admissible subset, then I have phase shift solutions. Right. So so I have to sit in this invariant subspace of the subgroup.
Well, if okay.
I'm trying to figure out what causes what, and I should have asked the question 15 minutes ago, but
Right.
you said now we're
No. I'm glad I gave you the opportunity, and when I'm not glad, I'll stop answering the question. we are writing down a menu of possibilities for all admissible vector fields. So the theorem is for admissible vector fields for the given network, the only kinds of phase shift synchrony that can occur are the ones that are associated with these symmetries.
Right.
We can also say that for every one of these rigid phase shift synchronies, there is a vector field which has a periodic solution that exhibits what we want. But we are not saying, definitely not saying, that every vector field has every kind of periodic solution. And you can have a periodic solution which has some kind of, it doesn't have any rigid phase shift. So,
But you still have the symmetry in the vector field. Yeah. Okay, great, thanks.
yeah. And that's important. I mean, it's going to be especially important in talking about the rivalry that we get this cleared up a little bit. Okay, so binocular rivalry is a standard psychophysics experiment. I'm sort of curious, how many of you know what binocular rivalry is? Great, okay, so I get to try to explain it. Imagine the following experiment. You have some sort of cardboard between your eyes, and now somebody shows you two pictures, one to your right eye and one to your left eye, and they are not the same picture. Such as, left eye gets this vertical grading red, right eye gets horizontal grading yellow. And then the experimenter, you're the subject, asks, well, what do you perceive? Not a question of what you see. One eye is seeing one image, the other eye is seeing the other image. What do you perceive? Answer, in most of these cases, you see one image, then the other, one, then the other. It alternates back and forth, and you cannot stop it. Okay? It does not oscillate periodically, first question that somebody might ask, but you keep alternating. Nevertheless, many people, when analyzing binocular rivalry, assume they are looking for periodic solutions. And that's a good way to go to begin with. So, and that is the way we will be going. So, without questioning that assumption too hard, we're going to be looking for periodic solutions. Now, how do you get back and forth between alternation? I claim this two-node network gives you the whole story. So let me give you an example of the kind of different, I will violate one of my principles when talking about differential equations to actually write one down. In this case, the standard way that people think about it is that you have in your brain somewhere groups of neurons, maybe a single neuron, which is, well, really groups of neurons, and that they're oscillating at some average rate. So they're called rate models. And the rate changes depending on the input to, in this case, from your eye. So eye is the input for either interpretation of eye. Anyway, the idea is that there are two of these groups, and you have this activity variable, AE, and I don't know why they use E, but we followed on, and AH is a fatigue variable. It sort of modulates the activity variable. But the activity variable is the important one. Think of it as the voltage in the neuron. And the spiking frequency. Then, if AE is bigger than BE, you perceive percept A. If BE is bigger than AE, you perceive percept B. That's the way these models go. And there's lots of people. This is a short list. Who have studied these particular equations. and for a long time. And I'm not going to go into whether they're good equations or they're less good. I just want to say this is the kind of thing that a lot of people do when studying binocular rivalry. So what do you get as possible solutions? Well, with a two-node identical cell network, we know the answer, because I've been prattling on about it for the last half hour. You can get solutions where the two nodes are doing exactly the same thing. They're synchronous. This is called the fusion state. One imagines that the two images are somehow superimposed, but it's a little bit unclear exactly what a fusion state would be. So if you have the two directions, the gratings, maybe you get a sort of square overlay with some funny colors going on. In short, interpreting the fusion state isn't so clear, but you can also get equilibria where one state is bigger than the other. And that's called winner-take-all. And the idea is if you had such an equilibrium, you would see that one, you would perceive that one state, and that is not what happens in the binocular rivalry experiments. But a third kind of solution is one that you can get, in fact, in the equations by Hopf bifurcation, but we know that such things, it's not surprising such things exist, where the two nodes are oscillating a half a period out of phase. And because they are oscillating a half a period out of phase, one of them, say the red one, is going to dominate the blue, but a half period later, blue must dominate red. You must get alternation when you have this kind of phase shift synchrony in the periodic solution. So this is called the rivalry solution, where periods of dominance alternate.
What happens with individuals who have two lenses, one sees a distance and the other sees close up? Is that your winner take all? Because with that, people do have those sorts of lenses.
No, but this is the brain, okay, I should say that rivalry is trying to analyze what happens when the brain gets contradictory information.
But this would be contradictory information.
Yeah.
But one eye gets shut off if you're reading.
Yeah.
The close.
Right.
Yeah.
Let's just keep to the idealized person who has two working eyes. So I'll take myself out of it, and I'm not going to go off into defects at the moment.
I think individuals who have cataracts have them removed and lenses put in, one that sees a distance and the other that sees close up.
Yeah.
And that works.
Yeah, I'm sure. But anyway, it's not this experiment. Since I'm not sure what happens, I'm going to try to answer it. But I will show you another set of rivalry experiments that without having to worry about whether your eyes aren't working, there's some really interesting things that happen. So Kovacs et al. 15 years ago or so did the following, or conceived of the following binocular rivalry experiment. To the left eye, they showed a picture of a monkey. To the right eye, a jungle scene which has text on it, so I call it text. And they asked, well, what do the subjects perceive? And they perceived monkey, text, that standard. Then they did something a little cleverer, maybe. They took the two pictures and cut them into 6 parts, and took the interchanged jungle, text, and monkey, so they alternated. And now showed these pictures to the working eye people and asked them what they perceive. And about half of the time, so for each individual, I'm not talking about overall individuals, but for each individual, about half of the time, they saw alternation between these two images. But for about a third of the time, they saw alternation between those two images. That is, they reconstructed the picture. So now it gets interesting. How in the world do these percepts come about? And what I want to do is use these ideas of periodic solutions with various kinds of spatial temporal symmetries to try to explain this phenomenon. Yeah.
Were they shown these pictures before they seen the other
No.
ones, or just seeing the half and half, they were able to reconstruct the
Correct.
picture? Okay.
They are similar idea. If you go by the Samsung 3D TV, and you see there's something different. There are two I see different.
Yeah.
I got one at home. Everybody.
Right. Okay. Yeah. So yeah, that yet another kind of experiment. Yeah.
What about the peripheral sides, left and right?
What about it?
What did they have on the left and right? Because that can affect what you see.
Yes, but well, I've just described what they did, and there was, you know, I don't think that actually has anything to do with the resolution. It's not a question of what's going on in the periphery. It's not a, you know, there's no trick here. You're being shown these two different images, and what you perceive is unexpected. That's the okay. So Hugh Wilson had a really neat idea for describing generalized rivalry. And his idea was that rivalry in the brain is between patterns, and patterns are defined by attributes. So let me try to explain a little bit of what he had in mind. You can imagine a system which has 5 attributes. These are 5 attribute columns that I've put here. And a pattern is a choice of, each attribute has a certain number of levels. So a pattern is a choice of level for each attribute. And you could imagine one such network having a number of different patterns that have been chosen or learned. So now, the idea is that you have inhibitory coupling between nodes in the same column. This is a kind of winner-take-all strategy, that if one node is bursting faster, the rate is bigger, AE is biggest, then it's going to suppress the dynamics in the other nodes. But the coupling between, and there's, by Hebbian learning, coupling between nodes in a given learned pattern, that is, you generate excitatory couplings between those nodes. Well, when you get through, you have created one of our networks. So with binocular rivalry, the assumption is that you get 2 learned patterns, one from each eye. And now you can look at the dynamics on these different networks. So this is an example where you have the purple and the blue patterns. Some nodes can be in common, but you get this kind of network structure. What we observe, we being Casey Diekman, Yunxiao Wang, and Tyler McMillan, and I, when we started looking at this thing, we said, well, yes, there are the learned patterns, but something that had been skipped over is that you can have patterns in the dynamics, that is, the activity variables dominating in each column, making a pattern which was not a learned pattern. And we call those patterns derived patterns. And if you use the standard rate models, then these derived patterns are always unstable. Well, we don't believe that the standard rate models are actually the way to go anyway. We would rather take the structure of the differential equations, say, well, what kinds of solutions can you get, especially what can you get from bifurcation from a fusion state, a maximal fusion state. That's a standard symmetry breaking trick to begin with. Okay, so let's try to create a Wilson network for this scrambled monkey text experiment. The rectangle has been divided into 6 regions, but a white and a black region, a subregion. In this picture, over the, I guess it's blue, over the blue region is text, over the white region is monkey. In this picture, over the blue region is monkey, over the white region is text. So we said, let's think of a Wilson network as having 2 attributes, the kind of picture that's in the blue area, the kind of picture that's in the white area. What are the learned patterns? Monkey in blue, text in white. text in blue, monkey in white. So there's the excitatory coupling. This is the Wilson network that we propose to think about this monkey text experiment. Well, in fact, this network has 4 kinds of patterns, 2 learned and 2 derived. The blue here means that these 2 are dominant. That's the one of the scrambled images. The green is the other scrambled image being in dominance. Red means that monkey here and monkey there are dominant, so you see all monkey. Here you see black, which is, if black is dominant in both cases, you get text over here. Now, it's not hard to show, however, that in the differential equations, you can actually get solutions where you get alternating periods of dominance between the scrambled images, that's the blue and green, but you can also get alternating periods of dominance in periodic solutions where you go between the 2 derived patterns. And this is exactly what's seen in the experiment. So by taking this Wilson idea, constructing networks, asking, well, what kinds of periodic solutions can come up? What are their phase shift synchronies? We can start to piece together. Okay, now Kovacs et al. Had another.
But you also had a third type of solution where they, half the time saw one pattern and then a third of the time they saw.
No, I said half of the time they oscillated between the learned patterns, and a third of the time they oscillated between the derived patterns.
So they don't go.
And there were some leftover things which may have been fusion.
So they're switching between one periodic pattern and another periodic pattern.
That's right, exactly. So they also did this experiment where they showed 24 dots. Half are red and half are green, and I'll ask you to count them if you wish. But the main thing that I want to point out is if it's red over here, it's green over here, or green over here, it's red over there. So it's sort of like the scrambled image. And they asked people what they perceived, and they perceived about half the time alternation between these 2 images, and some fraction of the time alternation between that seems very reasonable given the monkey text. But then they did another experiment. They showed people the pure color dot experiment and said, what did you see here? And they said, we see alternation between these, and we see alternation between the mixed images. Now, this ain't like the monkey text experiment. So, well, this paper caused a little bit of a stir in the psychophysics community of how to understand where these things are coming from. And Tong, Meng, and Blake wrote a review article in which they said, well, instead of worrying about 24 dots, let's look at the middle 4 dots and just think of this experiment. So what I'm going to describe to you is an experiment which has not yet been performed to my knowledge. And that is, let's look at 4 red dots and 4 green dots, and let's see what the Wilson network would be for this. You could also imagine that the answer should be that you get alternation between the pure color dots and between the scrambled dot patterns or the derived patterns. Okay. The 4 dots, we said, well, there are 4 attributes in describing this pattern. It is the color of the dot in the upper left position, the lower left, lower right, and upper right. Each of those attributes has 2 levels, red or green. The network is when you learn the red pattern, you get excitatory couplings here. When you learn the green pattern, you get excitatory couplings here. Now, a feature of Hebbian learning, or at least an interpretation of Hebb's learning algorithm, is that the nearest neighbor dots would be more strongly coupled than the further afield ones. So we assume that so this is now a add-on to Wilson's theory to say in the network you can have excitatory couplings, but they may not all be the same. And in this, we put this in. And when we do, the network has D4 symmetry, the symmetry of the square, plus up-down symmetry, that's the Z2 row. Now, if you start off with a maximally fused state, that is the fixed point space of this whole group, it's a transitive group, it's just all nodes are equal. And we ask, well, what kinds of solutions do you get bifurcating from there? And the answer is you get exactly what you'd expect. You get alternation between these states, you get alternation between these states, and you get some other possibilities. My favorite is a rotating wave. Well, there's a prediction. But this experiment hasn't been done. Will people actually perceive this kind of rotating wave? That's another kind of solution which would come out of this network. But what is perhaps interesting just from what we know about the experiments, if you take the scrambled dot experiment, then the learned patterns are red to green to red to green back again, or red to green to red to green. If you invert the levels in 2 of the 4 columns, then you can see you get exactly the same network that we had before. So you should get exactly the same solutions. So that means that whether you show them the scrambled dot experiments or the conventional pure dot experiments, you should expect the same sets of solutions to come about. And that's what indeed is observed. I have a couple more minutes. I'd just like to show you another of these surprising experiments. So you have vertical grading with gray and pink. You have a horizontal grading with green and gray. What would you expect to see? Well, what would you need in a Wilson network to describe these images, left eye, right eye? Well, we said you need something that says the grading direction, and you have to choose 2 colors. So we should have 3 attributes, 1 grading, 2 colors, and this is what we did. We put together one set of nodes. It gives you the grading direction, horizontal or vertical. The others give you 2 choices of colors. Boy, did this not come out. Yeah, that's okay. Then the horizontal had green and gray. The vertical had gray and pink. So that's where the excitatory couplings come from. I'll save you some effort. This has some symmetry. I'm not going to go through it. But what I would like to say is that you get 2 kinds of solutions coming out of this. One which is going to alternate between the original images with some question of whether this could go horizontal before it changes color. And then go back. So there's a little bit of wiggle room there. But the other thing that you get is the possibility of a green and gray, a pink and green with either horizontal or vertical grading. And this is what people actually said they saw from the experiments. The original pictures plus pink and green and gray and green coming out. So you can, even in advance, start to figure out what the percepts are going to be. And I was going to end with one other one, which I'll just tell you. If you do 3-dot experiments, you get different answers than if you do 4-dot experiments. And this is something which can really be tested. So what I'd like to suggest is that we have an algorithm, whether it's right or not remains to be seen, and it's certainly on higher level function of how you might figure out what the percepts are going to be given certain inputs to the 2 eyes in a rivalry experiment. And a lot of people involved in what I was talking about today. I mentioned Ian Stewart, Marcus Clavato, and Andrew Torek, and some of the general theory that I mentioned earlier about these balanced colorings and quotient networks. Luciano Buono, Jim Collins, Ian Stewart on the animal gates, David Romano and Yunjiao Wang, I mentioned on the phase shift synchrony theorem, and then Yunjiao, Casey Diekman, Tyler McMillan on these rivalry ideas. And thank you.
Questions?
So in your 4-dot experiment,
Yeah.
so you got 4 red and 4 green. Why can't you have a possibility of 1 red and 3 green?
You could.
But then your diagram would have to be more complicated, or? Yeah, right.
So when you had when the split is the red and green are equal on along the diagonals, which is what I want in the experiment, then in these possible solutions that come from the spatiotemporal symmetry, you don't get 1 and 3 as a standard thing. If you had S4 symmetry rather than D4, full permutation symmetry, which is keep the strength of the diagonal excitatory coupling the same as the adjacent, then you would get it. So that's in fact a test for which symmetry group is relevant, whether people are seeing.
How you feed the image to the eye? So one eye actually stare at one figure, right? Or alternatively?
No, it's set up so that each eye is able to see only one image.
Okay, so it's your brain that makes the composite
Yes.
image.
So these are percepts, these are perceived images, not things that are real.
So your eye actually make the 2 pictures and combine
Yeah.
it somewhere.
Yeah.
You mentioned in the beginning when you talked about this rivalry that it wasn't periodic,
Yeah.
but I didn't see where the non-periodicness came in and what you said afterwards.
Well, I
Because
said,
the synchronicity-
the next thing I said was we are going to model it by periodic
Oh,
solutions.
okay.
Yeah, yeah, now, there's a whole issue, and there's stochastic issues, there's all kinds of things. So people spend a lot of effort trying to decide what the frequency of switching is, and there's all kinds of things.
And does that aperiodicness have to do with whether you use your left or your right side dominantly, or?
I don't know. I mean, I honestly just don't know at this point. My guess is that there are two standard ways to model rivalry now. One is this differential equations way where the alternation is through periodic solutions. The other is through stochastic differential equations, and then different issues come up. And I think that's the way people will go.
But when you say not periodic, is it because it's rather chaotic, or not periodic, like one eye is more like aperiodic or biperiodic, so it's?
No, it follows, some people say a gamma function distribution, other people say it's another distribution. I have no idea. The main thing is that it doesn't appear to be a question of dominant eye or anything of that sort. So it's something that's going on in the brain.
Does the network structure or the symmetry tell you anything about the stability of the periodic solutions?
Yeah, good question. Yeah, good question. And the answer is no.
That's the details.
I mean, just the stability. So something that I did here was forget about stability. All I worried about was the possible existence. And there's 2 reasons for that. One, we wouldn't get anywhere if we didn't. So that's a kind of vaguely pragmatic way of approaching it. The other is that there's no reason because of this alternation and stuff to believe that you're looking at stable solutions anyway. So we just want to know what kinds of percepts might you really expect to see. And and there's some other experiments where the percepts are really very surprising. But they all seem to fit into this framework. Yeah, but so we were quite worried about how the mathematical neuroscientists would cotton to skipping over stability. And I would say there's a split. That a rather healthy percentage think if it ain't stable, it ain't worth looking at. But I think that's not the case. It's an important question.
This last comment. I don't think it's a good thing that if by some training you get rid of this, it is bad. Because 20 years ago I got dizziness, I can see ceiling spinning, everything like periodic. Now I'm overcome with this, I'm fine. You know, when you see things get mixed, it may not be a good thing.
Yeah, that's true. Some people may not react well to it.
Right,
Yeah, that's why there's OSHA and the biology, and they have to worry about people forms. So,
especially periodic.
yeah. So, but right now these images are just showing. By the way, I should say that look, the eyes are just one mode of input. You can also have auditory illusions and auditory rivalry, and one can imagine all other things. I maybe should end with one suggestion. Did you ever have trouble choosing what you wanted to eat in a restaurant? This is a question of rivalry. You have information which is, in a sense, contradictory. Some things are better here, some things are better there. It's not a clear winner. How do you make the choice? In decision theory, this is quite serious issues about how the brain comes to a decision. This is just a very vivid way of showing some of the possibilities. I think.
Speaking of stability, so will OSHA allow this experiment to run for a duration that would investigate whether or not there's kind of a convergence to a specific, instead of if the oscillations go away?
They won't. Do you know about the Necker cube? You take a cube and a standard image on the face, and you can't decide whether one face is behind or on top. Just stare at it. It's just, if you really force yourself, I'm going to make sure that face is on top, it may be a microsecond later before you actually switch. So there's something going on in the brain that which is beyond control.
Anything else? Okay, thank you.